the first time anybody thought of atom? Please tell us. When was it? Where was it? Why was it?
So let's not say first, because this always becomes a very contested thing.
This was over how many centuries or how many years?
These ideas persisted for a very, very long time.
Do you think these alchemists knew that they can never make gold, but to raise funding they had to give and should we do something like that to raise funding? Just go until we can make gold. So friends, today we have learned that before doing science, we need to colonize. तो पॉडकास्ट हमारे साथ चलो 2-4 देश को colonize करके आते हैं, फिर साइंस करेंगे हम लोग. Hello and welcome to Friendship with Science, a series of interviews with guests where we explore the world of Indian science, what's happening in it, have interesting conversations for you guys so you guys can learn more about science and scientists and get interested in science and become scientific. My name is Biswa. I am a comedian and I have with me Shashi Thutupalli. Correct?
Correct.
Okay, finally after 5 attempts I've got this name right. What am I getting wrong? Is Shashi Thutupalli?
No, you're getting it perfectly right.
Okay, but your reaction is not convincing.
Oh, I see. It's perfect.
Okay. So I have Shashi who claims to be a scientist. I have no further confirmation than his word on this. But Shashi is a scientist based out of Bangalore, NCBS, right? And he has been doing a lot of great work, is what I think. No, just joking. We are at the beautiful campus of Azim Premji University in Bangalore. Thanks to them, we are able to shoot this. We have a very, very interesting guest. Some call them the Einstein of Warsaw also. It has been heard. So to introduce our guest and say a little bit about the podcast, Shashi, please take it away.
Thank you, Biswa. So the idea of this conversation that we are having with many interesting guests is essentially to talk science and also try and bring out the Indian context, the doing of science in India and this sort of thing. But the main idea is to convey deep and fundamental ideas in science and scientific thinking. And leading us off today on this conversation will be our esteemed guest, Professor K Sridhar. Thank you so much for agreeing to do this. Professor Sridhar is a physicist by training. He got his BSc in Mumbai and also his PhD at the University of Mumbai. After which he spent years in London and Geneva at the CERN. And many years after which he came back and started as a faculty member at the TIFR, Tata Institute for Fundamental Research, Tata Institute of Fundamental Research in Mumbai. And Sridhar has made deep contributions in the broad area of theoretical high energy physics. And he has, in addition to his position at TIFR, also positions in many places in the world, Paris, London, and also at the CERN and so on. And Sridhar has, written a book in theoretical energy physics called Brane Worlds and Extra Dimensions, which is published by the Cambridge University Press. But Sridhar's personality and contributions don't quite end there. He is also a novelist. So he has written a very interesting book called Twice Written, based in Mumbai. Bombay, that's right. It predates the Mumbai, yeah. But he just told me also that he has an even more interesting book perhaps coming out, Ajita. So look out for... Book your copy right now. Yeah. So Sridhar, thank you so much for talking to us. I mean, I'm really overwhelmed, I think. So it will take me a little while to get going. Yeah, so I think we are going to talk about particle physics.
Yeah.
Right. So that's where we are going to start. No, that's where we're going to end.
Yeah.
But basically I want to see particle physics
as the culmination of this long history of atomism. So let's talk about atomism today.
Yeah.
And, you know.
Yeah, I think we should start from the beginning only.
Okay.
Before, like the first time anybody thought of atom. Please tell us. When was it? Where was it? Why was it?
Yeah, so let's not say first, because this always becomes a very contested thing. Okay. And in science and in other areas of academics, this is a perennial problem. So, but let's say, yeah, we go back to origins of atomism and early days of it. And why these ideas came about is more interesting, actually. It's interesting that the idea of an atom is really a Greek word. It comes from atomos. Tomos is to divide, and atomos is that which cannot be divided. Okay, so like tomos, dichotomy, is splitting up into two, or trichotomy splitting up into three. But atomos means you cannot split it up. So the basic unit, the fundamental unit, is called the atom. And it's in this sense I want to keep using the word atom today. Okay, if we talk about atoms in physics, or if we talk about chemistry and how atoms appear there, but we can also use the word atoms more liberally to mean the particles today that we know in particle physics. So basically I'm saying, if you go to the etymology of the word atom, so anything that cannot be split up, we'll call it an atom. Okay. And so this idea actually, as I said, goes back to the Greeks, but there was this very, very fertile and interesting connection between Greece, Persia, and India, the three great civilizations at that time. I'm using all these terms, Greece, Persia, and India, in civilizational terms, not in terms of country, nation, or anything like that. So these ideas moved across fairly rapidly. If you think of it now, it's quite amazing how quickly people were talking of the same things. And that's again the reason why getting into this who did it first is a bit, it's really a worthless exercise in some sense, because what is exciting is that this was part of a larger intellectual conversation that was happening across civilizations. And people were finding these ideas useful. That's why they were coming up with this. Okay. Of course, each civilization then brings its own context. There are things it places it within its own historical, philosophical, cultural context, and so on. But in Greece itself, the ideas of Democritus and Leucippus were the first atomists. They came as a response to these philosophers you probably know, Parmenides and Heraclitus. These were the two great Greek philosophers, and they represented two poles in the philosophy of Greece. One talked about being. Parmenides said that everything is permanent as it is, and it is being. A very allied concept is the concept of Brahman in Indian philosophy. So he says nothing changes. There is only one universal substance, and that substance is being. And in contrast, Heraclitus was refusing to accept that and saying that everything is in a state of flux. And in fact, he is the person who made the famous statement that you cannot step into the same river twice. And so he said that things are all the time changing and so on. So the atomists came in, and one way to think of the atomists is to say that they came in to resolve this tension between these two positions of being and becoming by saying that if you look at the phenomenal world, the world that we see around us, it is always in a state of change. That is true. But there is a substratum below this, and there is another deeper layer of matter below this. And this is the world of atoms, that everything is made up of atoms. So I see this shelf here, I see that plant there, I see you, I see myself. We are all made up of the same stuff, we are all made up of these atoms. And these atoms are eternal. They can never be created or destroyed. They are permanently there. So they are the being of Parmenides. But they create worlds which are constantly changing, the worlds of Heraclitus. So atomism managed to resolve the tension between these two very polar. Also, it kind of atomism.
Sorry, Sridhar, just to interrupt you there a little bit. You're saying that it resolved this tension, but somehow that means that I can see why once the being side of the argument.
That's something we'll come to later. It's this idea of emergence.
I have not understood your question.
Oh, okay.
What are you saying?
Right, good. So what I'm saying, so he said that now there are these two schools of thought, so to speak. One saying there's the being and the other becoming. So if someone comes in the intermediate as saying, I will bridge you both and I will propose this thing, what's called an atom, which everything is made of.
Yeah.
The being side might say, okay, this is what we are made of and that is the being, whatever. But the becoming side, which is saying that, there is something more coming out, cannot readily accept this because, if I take, and the other thing that he just said was,
this tension persists down to till today.
Yeah.
Because on the one side are the physicists who work on fundamental things, and then on the other side are the biologists. And this, it's mean it also very seriously.
I know exactly
if you take atoms of physics, let's not even go to the level of particles. But okay, so from particles you get atoms eventually. But you put these atoms together, you form molecules. And now, from this up to this point, we all get it.
Yeah.
From these molecules, something strange happens. Then you start studying some subject which you said you did very well in, called organic chemistry or something.
Yeah.
You didn't miss that chance to tell us that. So anyway, I flunked all my chemistry. So just saying. Where does this transition happen? Where you have inanimate atoms, there's no life, there's no consciousness, there's nothing. And suddenly on the other side, the biologists are talking of life and consciousness. And there is some link, right? I mean, we believe there's a link between the two because if you're synthesizing these, putting some complex protein molecules and then stringing millions of them, and then something happens. What exactly, we still don't know. But these are now talked about in this big paradigm in biology and physics, which is called emergence. That something as a property emerges out of. So the life and consciousness are emergent properties that emerge out of just putting chunks of inanimate matter together. So
I find it very interesting when you said that this atomism idea somehow seemed to appease both sides.
Yes.
And I'm very curious what the becoming side of the school.
No, but this question did prop up then. I think there were some I wouldn't claim that they were actually talking of emergent phenomena at that time.
Right.
But a grain of these ideas of emergence already existed. In fact, the Charvaka philosophers have actually talked about how if you take, it is simply, if you take things at an elementary level, then it's just matter, just like our quarks and leptons and so on. But if you start putting these together and make composites of this matter, then life and mind and consciousness, all these emerge as emergent phenomena. This thought is already somewhat implicitly there at least, not very explicit.
Maybe Biswa, I can make it slightly more concrete for you. So let's say there's molecules of water. Water flows, okay? Because it flows, it has this property of viscosity. There's a resistance to flow. What is the viscosity of a single molecule of water? The concept even doesn't exist. It arises only when you have a sufficient number of molecules.
Is this fuzzy logic type of thing?
It's not. No, I don't think it's fuzzy logic. I don't think it's fuzzy logic. I think what we're trying to say here is that there is an idea which doesn't even exist on some scale. There's a property which doesn't even exist on some scale, right? So if I take, let's say, molecules which are comprising you and I and put it out on the table, we won't necessarily call that living. But somehow when a sufficient number of them have come in an interesting configuration, something called life suddenly emerges. Yeah? That's the idea.
You can have all the words of a joke, but they're not funny.
Exactly. Exactly.
Yeah, jokes are definitely an emergent phenomenon. Because in fact, not just the words, but you string it into sentences. And it is possible to be very droll about it and not get the joke. So how is it that someone smart like Shashi gets the joke, but someone dumb like me doesn't get the joke? No, because you're saying the same line, and let us assume that all the words that you have said and the context that you're saying is all known to both of us. But still, there is something that he gets which I don't get. And that's, but a very nice example of this emergence. I thought of coming to this in the end, but let's do it the way it flows. I may have mentioned it that day in passing. But imagine that you make a model of a brain. Okay, so I'm trying to replicate a human brain. Okay, so human brains, I know, is made of neurons. Even as a physicist, even I know that it is made of neurons. So you put together a huge complex array of neurons, of integrated circuits, right? And each of them fires. Inside that integrated circuit, there are several configurations of things which fire like neurons. And this, I have complicated this enough to make it work exactly like the human brain does. Okay? Now, we'll all agree that this is working like a brain. Now, I ask you, this is a brain, but is this a mind? For example, can it make a choice? Can it vote for somebody in elections? Can it order an ice cream? Can it be perverse? Can it pun on words? All those kind of questions. This is all feeds into AI, of course, and big debates around that now. But the basic question is, the basic issue is that there are people who are divided on this. That some people believe that you just put together these circuits and consciousness and self-awareness, all that emerges out of this. Is it. That's all you need. You need the basic substrate, and all those things come out of it. I mean, emerge out of it.
Got it.
Okay. Whereas the others, it's not settled. There are others who believe that is not the case. There is something else you need to add to this. ये सब लगा के ऊपर से और कुछ तड़का देना पड़ेगा. So that tadka till you put, there is no consciousness. So this is a question. This is attracting people in various areas of academics today. And I think what will emerge before some clarity on this emerges, I think what will emerge is some new areas of work. Because it's going to be very, very multidisciplinary.
That's very interesting. It's like road is there, one car is going, then 2 cars, 3 cars, then 10 cars, suddenly traffic emerges.
Exactly. Or a jam emerges.
Yeah, jam emerges.
Exactly. That's exactly.
Or the other example of what distinguishes a small, group of homes somewhere out in the, farmhouses in the outskirts, and a city. What makes Warsaw, right? You and me are both from there. And we know something magical is happening. What makes it magic? So that thing is something that you don't put in. It emerges on its own. You just have to get enough of it for something to emerge.
That's amazing. It's like one atom of this might not be blue, but the entire thing
colors
becomes blue, something like that.
Okay, yeah, that's the next question that atomists had to tackle, and they started tackling this at that time, and they came up with different answers to it. So, are blue atoms of a blue material blue? So, are there blue atoms and red atoms? And salt atoms and sugar atoms and, all kinds of things. Some bit of economy had already happened even at that time, that people had started thinking of elements. So even if they didn't think of atoms, or even if they didn't subscribe to atoms, many philosophies and many different systems of thought accepted the notion of elements. And this is true again in all these civilizations. Okay. And in India, they were called Panchamahabhutas, the 5 elements. The 5 elements were water, air, we know that, earth, sky. And so the thing is, then you reduce your effort. You don't have to make atoms of everything, but you just make atoms of these 5 elements. So that's what early attempts were. So in fact, in India, one of the strongest atomistic schools was one of the orthodox schools of philosophy. Orthodox meaning, okay, Indian philosophical systems in 500 BC were divided into orthodox systems, which were the ones which accepted the authority of the Vedas, and the heterodox systems which would not. By authority of Vedas means in one set they believed that you could settle an argument by saying the Vedas say so. The others thought of the Vedas more as useful material where you can go and get a lot of information, knowledge from. But you cannot use that to settle an argument. You can refer to the Vedas for a lot of things, but you cannot conclude by saying that is written in the Vedas. So this was really the difference between these two camps. So, but in this orthodox system, there were 6 schools of philosophy, of which one school of philosophy was a very realist, took a very realist position, assumed that the world outside actually exists and that we can analyze the world as human beings. And they went about doing it in a very systematic way, which is very similar to modern physics and chemistry, trying to understand everything in terms of those elements and then those elements in terms of atoms and so on and so forth. So this this group, I don't know whether I mentioned, they were called Vaisheshikas. Okay, so these, sorry, what was the thought I was holding on to earlier? Where did this conversation start?
You and atoms are, and then elements.
Yes.
So we are talking about so this categorization.
Yes. So for them, for the Vaisheshikas, they actually tried to do a little bit of this. So they were like atoms of water, atoms of
fire,
these atoms of fire, and so on. In Greece, Democritus and others were actually trying to do this differently, and that is, in a sense, more related to a modern idea of an atom, where they were saying the atoms are all the same, but the way these atoms lock up with each other, and so these atoms had different ways of interlocking with each other, and in this process of interlocking, they create different combinations and so on. But the Vaisheshikas also had some ideas of, not the Vaisheshikas, the Jains. The Jain philosophers also, Jainism is an atomistic philosophy. And they had ideas of valency, for example, plus and minus, how atoms come together. Some notion of, I'm not saying modern valency, but some ideas similar to that. But what I find fascinating about Jains, and there are some special schools of Buddhist thought which have atomistic basis, in those I find it fascinating that they divided matter into gross matter and subtle matter. Okay, so gross matter was also atoms, which gross matter was made up of water, fire, and those things. But they also had subtle matter, which was made of atoms. So, for example, in Jainism, they talk of atoms of karma. So, karma is atomistic in Jainism, and even in these Buddhist schools, karma is atomistic. Why they did that is because, karma is something, so they don't even believe in the existence, like, that Buddhism doesn't talk of a self. It's a momentary thing, the self as a permanent thing which is subsisting all the time, that idea is given up in Buddhism. But they still had this idea of births and deaths, because the circle of karma has to complete. Because if you do something or if you desire something, that has to play out completely in this chain of cause and effects in karma. And the reason they thought of atomistic basis for karma is because atoms cannot be destroyed. Human beings can die. Now, in the orthodox systems, if the human being dies, there is something called the Atman, the self, which survives, the soul or self, that survives and goes to the next birth. But in these systems where you don't talk of a self and you say that that self itself is an idea that you have to give up on, then what is it that transits from this life to the next life? And because atoms don't get destroyed, the atoms of karma don't get destroyed. So your karma actually breaks up into atoms, gets transferred into your account in the next life, and you start your account book all over again. In the So it's actually this kind of psychological and traits and karma and so on, the way they carry forward, I think that has a nice link with genetics, because again there you're talking of
the unit,
the basic genes in that case becomes the atoms of biology, if you like, and how things get transferred across generations is because of these units doing something in a very complicated way, which I don't understand, but let's say people like Shashi do understand. So that it speaks nicely to. I just find this, and I mean, I certainly don't want to say these ideas were all there from 500 BC. Some germs of this idea, many of those wrong, but deliciously wrong.
Sure.
Okay.
And so, Sridhar, just a question here. So, some of these could have come simply because of pure thought, right? I've dreamed this situation, or was that the case in all these ancient discussions, or was there also some evidence that they were basing these kinds of things on?
It is certainly true that the Vaisheshika tradition plays a lot of emphasis on observation, of experimenting, and so on. So, Vaisheshika, so in these 6 systems, they come hand in hand with another. There are 3 pairs of systems. So, Vaisheshika comes hand in hand with a system called Nyaya. So, Nyaya was logic. So there was that logic and, understanding things through understanding the structure of arguments and thought. That was the Nyayika way of things. And Nyaya was a corroborating theory of the Vaisheshika, which was largely a realist physical position and placed a lot of emphasis on empirical. In those days, whatever empirical meant at that time.
Sorry, I had a very dumb question. But is atom and Atma 2 related words by any chance?
That's a good question if you ask me. Not really.
Okay.
But it's a good question because, as I said, atom is something that cannot be divided, and the Atma is also something, is like a unit, if you like. There could be, I'm not aware of whether there's an...
Got it. If you know, please write in the comment section. Don't spread wrong knowledge will not be accepted, but please do check and let us know. Okay. Sorry, so we are done, I think, with the ancient aspect of it. And this was over how many centuries or how many years, you would say?
These ideas persisted for a very, very long time. Some of them actually even make it into what look like religious discussion, religious or let's say theological. Some of it becomes very metaphysical. So these things get talked about as though they are some not physical units, but something quite different from physical, and so on. So these traditions continue, and civilizations change, and some civilizations take a backward step, other civilizations come up in their place. So when in the great days of Baghdad, about 1200 years ago, these ideas of atomism were also very current in Baghdad at that time and so on. And so it persisted and came down to Europe and 17th, 18th century Europe and so on. So that's where it started a new story. And, so we can take it from there if you like.
I was just thinking, like, maybe not the idea of atoms, but when they start purifying metals, like, they must have understood that gold is different from iron, or like bronze is obviously alloy. But like copper, by melting the earth, they were finding so much stuff. Was there any idea that these might be the elements, or does that idea come much later?
So there, that the whole subject of alchemy developed, and a lot of the roots of modern chemistry and some parts of physics actually have its root. I mean, those roots are in alchemy, and alchemy was the attempt. The goal of alchemy was to, create gold out of base metals, or one of the goals, if you like. And therefore, you have to spend a lot of time with base metals, doing, things which these days we call labs and experiments and so on. And they were doing that. So that knowledge, what that entire process of smelting and firing and doing things with their ovens, I think the gold that they really derived was that huge amount of empirical knowledge, which got transmitted and then used completely differently in chemistry. But that definitely fueled a lot of growth in chemistry later. Yeah. So these ideas, you're right, these ideas of elements also have their origins there. And I think this thing that we didn't arrive at knowing all these elements all at once. Then the ancient idea of elements was already around, that there are 5 elements, or some said 4, some said 5. Okay. But people were willing to give that up by the, because of the fact that they had much more of an understanding of things like metallurgy, for example. On the one hand, they had a much more intimate knowledge of herbs and medicines on the other. A lot of these actual doings allow you to get better information about all this. So they were willing to give up the idea that these are the 5 elements, but the conceptual framework of elements is something that they held on to. And that process was then of discovering what could be elements and what are not elements, what are compounds and what are elements. How do you understand that and so on.
Do you think these alchemists knew that they can never make gold, but to raise funding they had to give and should we do something like that to raise funding, just go until we can make gold?
No, I think they were more honest than today's scientists, really.
Okay.
Off the record.
Yeah. So I think we have covered pretty much the ancient and medieval ideas. Or there's something like
there is some timeline that we have covered.
Yeah. What happened next in this industry?
No, so I think let's move forward. This history is very complicated, first of all. So, I gave some version of it. Not so much to give the historical facts, but to just provide some conceptual links.
Yes.
Right? Because this is a very contested area and experts will deny all this and they will have some alternative way of looking at it. That's not where we want to go. But basically, how these ideas entered science is a good question to ask. And of course, everything started with Newton in science. Modern science began with Newton. And so, Newton's laws of motion, which every school kid actually gets familiar with, but few people actually understand it. what Newton achieved in one fell swoop, without getting into too many details, is that he could unify the motions of the heavens and motions on earth. And he could say that terrestrial motion and celestial motion are one and the same thing. This was not true in the case of Aristotle, for example. Why? Because if you take this and you roll it, at some point it stops. Okay? And so Aristotle said all motion on earth comes to a halt on its own. So that's how Aristotle used the word inertia, because he said all matter is sthula, actually. What is the Sanskrit word for it is sthula, and in Aristotle he calls it inertia. So he says all matter has inertia, and because of inertia it stops. He used the word inertia in the same way that we use it in normal English, right? And in order to keep it moving, we have to keep putting a force on it. Okay, and if you have a cart, then a horse is needed to pull it, and so on. But then they saw that the motions in heaven of the planets are very uniform. They don't seem to stop. They're going on. The sun is moving around us, moon is moving around us, day in and day out. So how is that happening? So again, scientific. You can't say it's not scientific. He proposed a very scientific theory, which is that the motion in heavens is different from the motion on earth. A terrestrial motion is governed by laws of inertia, but that matter is subtle matter. This is gross matter. And subtle matter has no inertia, and that is why. So he differentiated the celestial sphere from the terrestrial sphere. Okay. With Newton, all that went, because the same gravity that pulls the apple to the earth is the same gravity that keeps the earth around in its orbit around the sun, and so on. So it's the same laws of motion, universal law of gravity, as they call it, right? So that was one huge achievement. Wow. But even more, not just gravity, but for any kind of motion that you want to talk about, or even time evolution of a system, if you please, but let's not at the moment stretch it. Newton said that, give you a mathematical equation. You tell me what is the force, I plug the force in. You tell me the initial conditions, like where is this object and how. So if a bowler is bowling, you tell me all the forces that are acting on the ball, and you tell me, which is of course gravity, but it's also the kind of spin or the speed that the bowler has exerted on it, and all the angle and everything, right? But you give me the details of the force, and you tell me what is the point, where did the ball get released, at what point did the ball get released, and with what speed it was moving. If you do that, I'll give you the entire trajectory of the ball, which is quite a remarkable thing, right? I mean, at one point, and you can do this for anything. That was Newton's claim. Okay. So Newton became a god, literally. And in fact, Alexander Pope wrote about him that nature and nature's laws lay hidden in the night. The Lord said, let Newton be, and all was light. So he was really revered. So, and people wanted now to, cut to the 18th century, and people wanted to apply all these ideas to much larger domains. Again. But 18th century was also the era of colonization and industrialization. So they needed engines and machines for the industry. They needed engines and machines for war. So it was the thrust area. And like you said, the money is coming from there for that kind of research. So there were a lot of people who got interested in steam engines and study of engines in general. But then there were some nerdy kinds who said, let's look at the formal properties of engines, and the people who don't get the big share of money but are still interested in those kind of mathematical questions. So they wanted to describe the engine in formal terms and understand the engine completely. And by understanding, they meant, and these were largely French mathematicians and physicists, but some British mathematicians, physicists. And for
also by engineers.
Yeah. And who wanted to understand, by understand they meant, wanted to describe it in Newton's terms. Okay. And the terms that Newton had used in his theories were things which we are all familiar with, things like force and momentum and, energy and things like that.
Mass.
Mass, of course, yes. But when you're building an engine or you're an engineer tinkering with an engine, then the kind of things you're doing is talking about the gas inside an engine, so the pressure that it exerts on the walls. So you're talking about pressure, you're talking about the temperature of the gas and so on and so forth. So what do pressure and temperature and so on mean in Newton's terms? This is the kind of dictionary that they wanted to construct, okay? Translating ideas which we call macroscopic now, but macroscopic came because of this movement that happened in physics. So what do you do to measure temperature? You take a thermometer and dip it into the gas. And in that 1/2 a minute that you hold the thermometer inside, this gas is transferring its temperature to this mercury column that is there in the thermometer. So these brilliant men and women, few women unfortunately, visualized this gas as being made up of a huge number of many tiny particles. We won't say what particles they are, but let's say particles, let's call them atoms for the moment if you want. And these things are buzzing around inside the gas, and when the thermometer is inserted, these just go and keep hitting the walls of the thermometer. And in each such collision, these particles transfer their tiny amount of kinetic energy to the thermometer. It's a Newtonian collision. Okay. And what the thermometer is doing when you hold it in there for a minute is to do an average over all these different collisions. And it is giving you a record which is an average kinetic energy of all these particles inside the gas. Similarly, the pressure is the average force that these particles exert on the walls of the container. So by using these ideas of these particles, these atoms, these brilliant physicists could translate pressure and temperature into words like momentum and energy. Okay, so they got a Newtonian description. They could now actually work out those individual collisions. They could define something like an average and do it, and all that mathematics led eventually to the development of some beautiful areas of physics called thermodynamics and statistical mechanics and so on. But just look at what has happened in the process. In order to describe something that is right there in front of you, a gas which is hot, which is exerting pressure and all that, all these observable things, you have substituted, you have inserted now a layer of particles which you have not seen, just to be able to do this theoretical translation. Okay. Science moves in these very interesting ways. It's not enough to say that science is an empirical thing, everything eventually, inshallah, has to be observable. Okay. But in actual practice, in the day-to-day doing of science, it's a zigzag movement. We go out of, what is observed to what is not observed, and so on and so forth.
There were many ideas being proposed at the time, right?
Yeah.
That heat is a fluid,
yes,
all of this kind of... Yes. So there were many competing thoughts, one of which is this.
No, I'm just, also it's a nice illustration of how science works, I think. Anyway, so from here, things eventually moved. So, of course, the amount of dramatic developments that were taking place in chemistry at that time, like you said, in trying to figure out what are the elements of chemistry and so on and so forth, that work started, and that led to a whole lot of understanding of chemicals. And actually, because to some extent you could do chemistry experiments, I think, correct me if I'm wrong, in controlled conditions in an easier way than in other subjects. Other areas like physics and biology, it's more difficult.
No, I think they had many more years of tinkering in this alchemy sense.
That
right?
is one thing.
They had this playful attitude from which came these techniques to play around with materials, right? And gases.
Exactly. So there was a lot of phenomenological experience that was built over centuries. But in addition, these things you could actually just see how mix these chemicals and see what combines with what in what proportions. And the fact that just like Pythagoras noticed, like we were talking about frequencies, and he noticed a certain pattern in terms of integers for the frequencies in a musical instrument. Like that, chemists started noticing some regularities. Only so much this concentration of this substance, chemical substance, will combine with that. So if you measure so many grams of this and so much, that is how you can combine it.
And classic example is again water. Right. So you need this proportion of hydrogen, this proportion of oxygen to give you water. So they had developed these empirical ideas of
and eventually the thing settled on how many elements are there. That there are elements, and these are the basic stuff of chemistry, and you combine these elements to make so for example, water is not an element like the ancients thought, but water is made up of hydrogen and oxygen.
How did they realize that?
Okay, so you can split up water. I don't know. One way of doing it is to split up water by doing an electrolysis experiment, right? You can collect hydrogen and oxygen separately. But how was the...
They knew, for example, that hydrogen was a flammable gas. Yeah, so this was the discovery of hydrogen. And then you start, I think these people were putting every material.
Just doing anything.
Yeah, just doing anything, right? Yeah, you're trying various things, and then you're lighting a lamp and asking, hey, is something combusting, something no. So it's a lot of inferential process that's going on, right?
A lot of back and forth.
Lot of trial and error, back and forth, and many mistakes, right? So this is not a linear process at all. Okay, it's not that I want to figure out what it's made of. You don't even know that there are some, smaller constituents, first of all, right? So you're playing around, suddenly, hey, this happened.
Who was funding them to play around? Sorry, just a question.
I don't think there was any scheme in, like funding, and so each one was doing their own thing. Maybe there were some guys who were interested in making gold from this chemistry, and they were giving some money to them.
See, some other guys some just kind playful. Of problems which were already seen as prominent,
right?
Found funders. Like in Europe, there are a lot of not just big emperors, but even smaller rulers and kings who thought that this could have some potential application. So they would fund it.
And the entire enterprise.
On the other hand, there were mathematical problems which were also open for prizes, for competitions, right? And that was a big tradition of that time, that someone would propose a problem and offer money for the solution, saying that if someone solves it, and many of the people who were doing high-level mathematics at that time were also moneyed people. So some of them were offering money from their own pockets. In other cases, Napoleon is famously said to have, offered money for solving several mathematical problems and so on. So that money was coming from those kind of sources. But then a lot of people were just doing it for the joy of discovery and so on.
And of course, the whole enterprise of thermodynamics, steam engines. Right? There was very utilitarian aspect to it. So.
Yeah, no, I was asking because for so long nothing was happening, and then suddenly there's an explosion of this, right? Like everybody studying everything kind of thing. Just trying to find out why.
Maybe. Or maybe we are looking at it that way. Like that. Okay, and what I'm giving you is the usual line. Okay. But so, for example, that when Newton wanted to wanted to actually put down the equations of motion, then he realized that the mathematics that was available at that time was not enough, and he had to develop something more than that, and that's how calculus came to be. And we also know of the fact that not just Newton but Leibniz also discovered calculus, and they fought over this, quite a bit. But now actually there are different readings in the history of mathematics, and people are now discovering that in fact there was this Italian guy who had anticipated both Newton and Leibniz much before their time. And then we now know of the Kerala school of mathematics, and how they actually explored this intersections of trigonometry and calculus, and got some, I won't say got all of calculus, but some very, very key results in calculus. And so it is never that something just comes out of nowhere. But then what happens is sometimes there is a context that gets provided, that there is a civilization, there's a country or nation which becomes more powerful at that time. There's more money flowing around. There's this general excitement about this. We know where that money came from, colonization, right? Yeah. So unfortunately, this history of science is mired in the history of colonies. So and there's much work now done on that also. So all that is that. I mean, we are not discussing all of that. We are just cutting to the main pictures.
I mean, a point to be made here also is, I guess, some of these efforts were on the fringes. It was not the main activity of the time.
Yeah.
Right. So maybe things like funding, etc., in the scale that we're talking about today, didn't exist, right?
So friends, today we have learned that before doing science, we need to colonize. So podcast बंद करो, हमारे साथ चलो, 2-4 देश को colonize करके आते हैं, फिर science करेंगे हम लोग. Okay, great. So this has happened. Sorry, I have an open mind. What to do?
Very open. Very fertile.
Nepal, Bhutan, watch out, we're coming. Okay, this will cut out. Okay, anyway. Now coming back, lots of sciences, they have, basically in sporadic bursts, they have figured out a lot of things to fit into Newton's system, right? Instead of looking at it, I mean, maybe there are competing theories also, you're saying. Then, where does this, and they're saying these particles and things are there, but I'm guessing at this point it's still theory, right? Yeah. And where does it get confirmed? Like when does the wide acceptance for the idea of atom comes?
Again, this was again probably another 120, 130 years of staying with these ideas, and developments were happening both within physics, development of statistical mechanics and so on. So those crude ideas that I described earlier, those became very sophisticated by the end of the 19th century. But also chemistry, that Mendeleev had put finally a periodic table and dramatically confirmed the existence of, predicted the existence of missing elements simply from the fact that those slots didn't have any, and those elements were later confirmed and put there. So the success of the periodic table, I mean, this actually allowed people to start thinking more carefully about what are the regularities and periodicities they see in the periodic table. What are the origins of that? If you look along one column of the periodic table, why do those elements behave the same? And again, it's numbers. So suddenly Pythagoras comes back, no matter what you do. You're talking of matter, you're talking of properties, you're talking of chemistry, physics, and then it seems to all reduce to some numbers. Okay, so some regularity of numbers shows up, and why is that happening? That is one kind of question, but that will be a very simplistic way of putting it, because there are lots of different things happening at that time. Okay, so people, another way of actually looking for elements, which became a very powerful method, was spectroscopy. Okay, so I mean, spectroscopy became a very powerful technique in the 1840s, 1850s. People like Kirchhoff and Fraunhofer and these guys. And what they did was also to turn their attention to light coming from distant objects, the sun or the stars and so on, and used spectroscopy. So now what you do is you have you have some substance, you know that it's some element. Okay, now you fire up that element, which emits radiation, and you look at the spectrum coming from there. So these elements usually have some lines on them. These are called absorption lines or emission lines, and that is the signature of that element. So looking at those lines in the spectrum helps you identify the element, and by your spectroscopic methods you can determine the wavelength of that radiation. So, but what they did was to compare the light coming from celestial objects, sun and stars, to look for the pattern of lines that are coming from them. And they found that, in fact, these were composed of the same kind of elements that you find on Earth. So this was another huge discovery. Because one is, we know elements in our neighborhood, in our proximity, on the Earth at the most. But how do we know about things that far away? The realization that the heavens are not made of some other material, but of the same kind of material that the elements on Earth are made of, was a very, very profound discovery. Okay. And elements like helium, for example, it was first discovered from the spectra of light coming from the sun.
Wow.
That's why helium is named after Helios. Helios is sun in Greek. Okay. So it was only later synthesized in labs on Earth.
Wow.
So it was a moment. It was a time of, I think, great discovery coming from different perspectives, different angles, using very, very disparate kind of tools, theoretical, experimental tools. All that was being developed, used. It was a time of, I think it was probably the golden age of discoveries in some sense. Probably, I would say between, let's say, the late 18th century to about 1935 or so. And after that, our kind of boring science took over.
Two questions. One you have already answered though, but I want a little bit more clarity. This periodic table that Mendel, right? Or Mendeleev, both different people. Mendel is peas.
Mendel is peas.
Mendeleev is periodic table. So he didn't know. Did he know or did he not know about the existence of atoms when he was creating it? What was he actually trying to do? Just similarities of elements he was arranging?
He was actually largely going about it from that point of view. But no one ever does this in a vacuum, frankly. Right. He may not have been an expert on atomic theories. He didn't contribute to anything in atomic theories that happened even immediately after his thing. But I think there is this kind of conceptual frameworks that exist. and those get passed on in science through informal conversations and so on and so forth. So, for example, I may have no expertise in the kind of work Shashi is doing, but over coffee he may tell me something. It may be vaguely relevant for what I'm doing, not exactly, but it may help trigger something in my mind because he has given me that bit of information. So I'm saying that conceptual idea of atoms and so on may have been at the back of Mendeleev's mind, but how exactly it is coming out was not obvious to him, definitely not obvious. And that was a whole journey which we'll go into now, which is what quantum mechanics was all about. Okay. And that actually started with...
Sorry, before you go to quantum.
Okay.
Sorry. A couple of questions. More is there. So he was just sitting with some elements, seeing what their properties are, arranging in a list, and then finally he was like, I think I have arranged them all.
I mean, I don't think he was working with the elements. He was taking a bunch of observations.
Okay. And it's just
trying to categorize. He's trying to
this
categorize.
One is very reactive. This one is also very reactive, like this he was doing.
So some similarities of, so in terms of that. And his work was essentially classifying the elements and putting in.
Got it. And anybody had tried this before him?
Yes, I'm not sure.
I don't know either, actually.
Okay.
I don't know either.
Okay, second question was this spectroscopy. I know you have explained, but just a more general understanding I want. There is an atom or something, let's call it some unit. You're basically putting light on it, or what are you throwing at it?
Yeah. So you can shine light on it.
Okay.
And then this atom gets excited so it basically absorbs energy. And then it goes to a higher energy state. And then it stays there for a bit and then radiates that energy, gets back to its original state. So that radiated energy you can look at. So this is
just visible light we're putting on it?
No, you're essentially energizing this system.
Oh, just energizing, and then it gives out light.
So it can be in any form.
It can be light, it can be
terms of heat.
So when you're heating up iron and it's
exactly.
That is
exactly.
So you're energizing.
So when you look at the light coming out of that heated metal, it is radiating in all spectrums. But it's a combination of wavelengths. So you put that through a spectrometer. That spectrometer analyzes the wavelengths. It splits it up by wavelengths. So what it gives you is an intensity versus wavelength plot. So you know that at this wavelength, it is giving so much. At this wavelength, it's giving so much.
Wow. And so when you look at this spectrum, it's basically like a fingerprint, a barcode. So you get these lines at some unique positions. Right? So if the composition of two distinct things that you're getting this spectrum from, these barcodes are identical, you'll say, you know what, they're comprised of the same constituent elements. That's the inference.
Got it. So let's say if you heat iron to some degree versus nickel to a different degree, then it won't be the same red, let's say?
Yeah.
Is that correct?
Sure.
Okay. And these are, I'm just giving examples of metals, but in case of gas, also hydrogen, you can just keep exciting and it'll radiate at some point?
So, so you can, for example, put it in some kind of tube, connect it to wires, and so that will like a discharge tube. And so there are different ways of exciting this, but eventually whatever light comes out, you analyze that. And
Got it. Sorry, I'm going to ask a dumb question again. But like we know, when you light a matchstick, it gives you a yellowish flame. But when you light a gas, it gives a blue flame. Or I don't know, if you light another thing, it might give a green flame also. I've seen a green flame, I don't remember where. But is this also related to the spectroscopy type of thing you're saying? Is this because you're really exciting some atoms and they're radiating energy here, no?
Yeah, I think here is a slightly more complicated thing because also it depends on the temperature that you reach, the kind of color that you see. Okay, of course it will depend on what is being burnt, which might also determine what temperature it reaches. And so in this particular case, it's a combination of all these which will give you that color. Right? But then if I analyze that radiation which is coming out and I split that up into its constituent, it will give you distinct peaks which come from the composition of that gas that's being burned.
Let me ask another way. The red hot iron and the fire that is burning, are they the same thing? Like the heat that is being radiated from the iron versus the wood burning the fire itself?
Right.
Is the fire the same as the red hot iron?
So what we are talking about in terms of the light that's coming out and being measured, you're right, it is indeed emitting light. But that light that we see is comprised of different wavelengths in different proportions. Okay.
Sorry, I'll ask it another way.
Okay.
Like you must have seen barbecue coal, right?
Yeah.
That is radiating red light.
Yeah.
Okay. I don't know why it's radiating, but it's radiating.
No, it's being heated.
Yeah.
So it's radiating. That's
but if you put kerosene on it, suddenly fire comes.
That's right.
Is that fire a different thing, or is it just hydrogen spectroscopy? I don't know what.
No, so in one case it's the coal that's actually emitting. In the other case, there is a gaseous vapor on top which is being energized and emitting.
Got it.
Right?
So even by analyzing that fire, you can tell what gas is there?
Yeah.
Wow.
That's exactly what Sridhar said, right? The star up there is basically a burning cloud of gas.
It's being fueled differently.
It's being fueled.
It's a fusion nuclear reactor that is up there, and that energies that is coming out of there, that radiation we are observing. And you also asked a slightly different question, and that of course is true, and we'll answer it parenthetically. Yes, you can actually go and look at different regions of the spectrum, not just the visible spectrum. Even though spectroscopy started there, but now you basically go and look at any part of the spectrum and you'll get different and complementary information about the same object that you're studying.
Wow. Got it. Last question on this. I'm promising last question.
You're really quizzing us on this.
Sorry, it's very interesting. Now you can look at the sun because it's burning and you can tell it's made of these elements. But can you look at Mars or another planet which is not radiating by itself and still draw the same conclusions? Because this way you can analyze stars. I understand that. But were they analyzing the stars or planets also?
Planets, it's a little more.
It's trickier because it's reflected light.
Okay.
It's not emission.
Got it.
Right? Yeah. So the light from the sun is
technically, the light that gets reflected from the surface of planet also interacts with the material of the surface, the material that constitutes the surface. In some sense, it does contain that some information. Not this kind of direct information. It contains some information which could be analyzed, but that is much trickier.
That's my. I mean, that work actually leads directly into Raman effect. And so that's how you probe materials. You shine it with something, and then you analyze what comes out when you shine something.
But if you're looking at a planet and the volcanic eruption, then you would know. Like if some
you would not know the composition of the planet as a whole, but whatever. Yeah, exactly.
Okay, I'm done. Sorry, we can now move forward.
Okay.
I guess this is also the time of, as you mentioned, the kinetic theory of gases, that description. There was Einstein. There was these ideas of motion of small objects. Many discussions about atoms or small particles comprising the materials around us. That's roughly the timeline.
And people had already, started getting some idea of the fact that there is something like an atom inside, and some idea of what the atom is constituted of, that some basic idea of electron, and these ideas were all just falling in place. There was, I mentioned Rutherford's experiment that he did with gold foil, where he shot alpha particles on gold foil. And he discovered that actually these alpha particles pass through the gold foil most of the time. But there are a few occasions where it just comes back and hits you. And he was very surprised. So basically what it suggested was whatever was inside at that elementary level, things were just going through, which means it was empty, except when there was a small chance of interacting with something. But that interaction was a huge interaction, so that this was getting shot back literally. So he was very surprised by these experiments.
He was quite dramatic in his description also, right?
Yes.
So it's like I'm shooting a bullet at a tissue paper.
And then
it's
bouncing back at, ricocheting from a tissue paper. And that is because the entire positive charge of an atom is concentrated right in the center, in a very, very tiny region. So for most of the time, these alpha particles are not interacting with it, they're just going past. But when it does, it is seeing all the entire positive charge. So if you have gold, it's a large amount of positive charge. And that is what is causing this big effect. So the idea that a picture of an atom was beginning to emerge, that, okay, you have a positive charge, protons. People had not yet discovered neutrons, but eventually that was also to come, and that was also put inside in the nucleus. And that there were these orbits around the nucleus where the electrons were orbiting. And this gets said very often, but I think in a program like this, it's a good idea to get some, a good thing to do is to get some idea of the scales involved. When we say orbit, how big is that orbit? When we say nucleus, how big is that nucleus? Okay. So if you, for example, so it's what, 10 raised to minus 8 centimeters, which means if I take a centimeter, and I take a centimeter division on a ruler, and if I divide that into 100 million divisions, then each such division will be the orbit of an, the first orbit of the hydrogen atom will be roughly in that range. Okay, so it's that tiny. Okay, now if I take this as my thing, the nucleus is another 10 raised to minus 7, which means, 10 raised to minus 5. So it's another 100,000 times smaller than so this is the kind of scales that are involved here. And so the information that you get, as we said, is from spectra. And now what happened was, if you say that all this positive charge is here, the negative charges are roaming around. Now negative charge is going in an orbit, means even it's moving around in an orbit, its direction is constantly changing, so there's acceleration. And because it is accelerating charge, and we know from electromagnetism that if a charge accelerates, it keeps radiating away energy. Okay, so this electron will keep losing energy because it's accelerating. It will keep losing energy, and it will spiral and fall into the nucleus. For one, there won't be any atoms because of this. And for another, more mundane consequence of that would be that in the spectrum of this atom, you would see a continuous line, because the energy is changing continuously as it spirals. It is becoming less and less and less till it finally becomes zero. But what we were saying earlier is that you don't see this continuous spectrum. You see very discrete spectrum. See very, very sharp lines. So people knew that something was totally wrong in this conception of that. So the picture of the atom was right, but the dynamics, what is the dynamics that holds this atom together, was completely wrong. And how does one say this? I think the best way is to talk about the uncertainty principle. Okay, so which is of course talked about a lot, so I'll still talk about it. And I like to talk about it in this way. So there's a whole lot of stuff that when people, you must have done some quantum mechanics in your IIT days, I'm sure.
No, I was biotechnology.
Oh, okay.
I have not done anything. Not knowing anything, guys.
No. So you've taken A class.
You know, but you must have heard of all these discussions about is electron a wave or is electron a particle,
yes.
and this and that, and wave-particle duality and this and that. Okay, one easy way, not easy, but one efficient way of understanding all this, and at least I like to put it this way, is, you know, what is a particle and what is a wave is something we need to first understand. Okay. So particles and waves are just two different kinds of conceptual models that physicists use. Okay. And frankly, physicists are very limited in their imagination, so these are the only two things that they know how to use. And what is a particle in physics? A particle is anything that gives you a definite answer to the question, where is it? Okay. If I say, where is the glass, I can point out and say, this is a glass, then I would call it a particle. Okay. So I'm using this in a guarded way because if I'm very, very close to the glass, and if I say, where is it? Is it here? Is it here? Is it here? Becomes a question. But if I'm sufficiently far away from the glass, I can point out to it and say, it's here. Okay. And so something which has a definite answer to that question, I would call it a particle. A wave, on the other hand, is something like if you have a wave on a string, that entire disturbance on the string is the wave. So there's no point in asking this question, where is it? It does not give you any definite answer to it. Okay. So these are two kinds of models, conceptual models that physicists have used, and used it in mathematical ways, but that's another matter. Okay. Now, the point is, when we are talking of electrons in an atom, physicists, because they didn't have anything better they could do, were trying to, so the idea was this. This is table, we are saying table is made up of atoms. Table is matter, so atom is matter. Atom is matter, so electron is matter. You know, and table has like these kind of very definite properties. It answers if I stand far enough from the table and say, where is the table? I can point and say, there it is. So similarly, I can go down. I should think that the electron also gives the same answer to that question, where is the electron? So I impose a particle picture on the electron, try to understand it as a particle. Okay. Now, if I want to understand this as a particle, and if it is a particle, everything will work out fine. Unfortunately, the electron is some kind of a transcendent entity. It's neither a particle nor a wave. That's the best way to think of it. It's described by some complicated mathematical function in quantum mechanics, which appears like a particle, sometimes like a wave, sometimes, and so on. But appears like is a way of saying, because that is our limitation in understanding. We impose either a particle picture or a wave picture on it. But it can be both. That is the whole point. Again. Now, if you say, where is the electron? Okay, suppose it's here in APU in this lab. Where is the electron? And young man like you, today when you say, where is the electron? What you do? You will go and open your phone and use Google Maps to do that. And you'll have first a large rectangle as big as Asia or something. And then that rectangle will zoom in and it will come to India, to Karnataka, to Bangalore, to this godforsaken place called the back of beyond Sarjapur. Okay. And you'll come into this lab and you'll then make the rectangle smaller and smaller and smaller. So your Google rectangle is becoming smaller. And inside the lab on that table where the experiment is, and there the electron is, and you start squeezing it. Till then the electron is well behaved. But just as you start squeezing it, the electron, because it's already also a wave, has a wavelength associated with it. So you reach the point where your rectangle is getting as tiny as this wavelength, it starts reacting.
Wow.
Say, tum mujhe daba rahe ho, you know.
Got it.
So it's like getting squeezed on a Bombay suburban train, which you have experienced surely. So the electron starts getting squeezed. So its wavelength starts reducing. And funnily, the wavelength of the electron is related very directly to its energy. So if you squeeze the wavelength of the electron, its energy starts going up, it becomes agitated and starts going around violently. So while you can, by squeezing this rectangle, get precise information on where the electron is, you don't know anything about its momentum now because it started wiggling around very violently inside this rectangle. Okay. So you cannot simultaneously get these two bits of information. If you try to get the position of the electron, then you lose completely the information on its speed or momentum. And similarly, if you try to get information on the momentum, then you lose information on where it is located. Because the information on the momentum means you will have to make the wavelength as big as possible. Then it becomes a wave, really. And then it doesn't give you a answer to the question, where is it? Okay, so this is how this uncertainty principle works. You cannot simultaneously do both of this. Now this atom, electron in the atom, which collapsed into the proton, which was ruining our universe, how do you save it? You save it because of uncertainty principle. Because if the electron loses energy, spirals and spirals, as the classical theory will tell you, and fall into the proton, into the nucleus, then it has reached a point where its energy has become zero and it is sitting on the nucleus. So you know its position and you know its moment. Its momentum is zero, its position is position of the nucleus. So you have violated the uncertainty principle, which you cannot. So if you try to locate the electron there on the nucleus, it will start reacting violently to it and starts pushing out. And eventually in this balance between position and momentum, it will end up in this orbit here and not sit on the nucleus. And that's how the stability of the atoms are ensured.
And we've reached the uncertainty principle, so we're taking a break here. Maybe there'll be part 2. But maybe there will not be. There's some uncertainty. No, definitely there is a part 2. So part 2 gets into particle physics really deeply. So have a tea, coffee, then come to part 2 with proper energy. Come, okay? See you there, and like, share, subscribe, like everything. Ring bell icon, bell ring icon, whatever is the thing that you gotta do, man. वो सब करके आओ, मिलते हैं पार्ट 2 में.